welcome all to the second part of the tutorial session on metal forming. We are in the course Basics of Mechanical Engineering 2 and I am Dr. Amandeep Singh Oberoi. Tutorial session metal forming. We have discussed forming mechanism, extrusion and drawing in the previous part of the tutorial. I will discuss in this tutorial the rolling and forging processes majorly. So, what is rolling? Let us try to recall the concept. Flat rolling involves rolling of slabs and sheets, where you can see here workpiece is given in green color and the roll is given in the gray color, and this is the rolling process where initial velocity or the entrance velocity is V0, the exit velocity is Vf, which is higher. So, Vf is always greater than V0 because this volume would stay same, the continuity equilibrium equation that we have been discussing. This is a simple flat rolling. These are known as roll mills. In flat rolling, the work is squeezed between two rolls so that its thickness is reduced by an amount called as draft. Draft is T0 minus Tf. So, draft, T0, Tf are all measured in millimeters. Draft may be expressed as a fraction of the starting stock thickness. So, there is a term known as reduction R, that is draft per unit the initial thickness. This is reduction R. Increase in the width of the work in rolling is termed as spreading, that is the roll, if it is spreading across, that also is W. So, let me come to further. The volume is always preserved, that is conservation of matter what is discussed. That means T0, W0, L0 is equal to Tf, Wf into Lf, that is volume stays same, where W0, L0 are the starting width and length, Wf, Lf are the final width and length respectively. So, here as I mentioned, V0 and Vf are the initial and the final velocities, and T0, W0, V0 is equal to Tf, Wf, Vf. Now, if theta and r are the arc angle made by the roller with the work and the radius of the roller, this is a neutral point where velocity of work Vr, that is surface velocity, roll speed in meters per second, that is V0 is less than Vr is less than Vf. So, we have Vr here, this is Vr, this is V0, this is Vf. Final velocity is higher as I mentioned. It is also mentioned that there is an intermediate velocity, that is surface velocity, when the rolling is actually happening here. At no slip point and the roller is equal, and on either side of this point slipping and friction occurs between the roll and work. The amount of slip between the rolls and the work is known as forward slip. That is also given. Slip is equal to the difference between the final and the neutral velocity per unit the neutral velocity. We have true strain, which is given by the log of the ratio of the thicknesses which are initial and the final thickness. Also, there is a maximum possible draft equation which is equal to nu square r. Here nu is the coefficient of friction and capital R is the radius of the roll. The equation indicates that if friction were 0, draft would be 0 and it would be impossible to accomplish the rolling operation. The rolling peak pressure is at the neutral point. This is already discussed here. Let me come to the problem statement where it is given. In a rolling process, sheet of 25 millimeter thickness is rolled to 20 millimeter thickness, which means the initial and the final thickness is given. I will put it as T0 is given, Tf is given. T0 is 25 millimeters and Tf is 20 millimeters. We have been given the roll diameter as 600 millimeters, which means I will put it as D is equal to 600 millimeters, which means R is 300 millimeters. it is roll radius, and the speed of the rolls is given in RPM. I will put it as n is equal to 100 rotations per minute. What is the roll strip contact length? Contact length is question mark. L contact length is equal to under root of R into draft. To find this, let me first find draft. Draft D is equal to T naught minus Tf. This is equal to 25 minus 20. This is 5 millimeters. And roll radius R is equal to 300 millimeters. Therefore, this roll length turns out to be under root of 300 into 5, that is under root of 1500, which is equal to 38.72 millimeters. Very simple calculations. The roll strip contact length is given by this relation. Another problem statement which says a 4 mm thick sheet is rolled with 300 millimeter diameter rolls to reduce thickness without any change in its width. There is no change in width. Friction coefficient at the work roll interface is 0.1. What is the minimum possible thickness of the sheet that can be produced in a single pass? Minimum possible thickness. This is again an interesting problem where we have been given the initial thickness, it is T naught. T naught is equal to 4 millimeters. We have been given the diameter, D is equal to 300 millimeters, which means radius is equal to 150 millimeters. This is the radius of the roll, and we have been given value of mu, that is the coefficient of friction, as 0.1. Now Tf, its final thickness, is to be found. Final thickness, that is minimum possible. Now I will use the relation draft is equal to nu square R, which means T naught minus Tf is equal to nu square R. Therefore, to find Tf, I can put it as T naught minus mu square R. Let me put the values. T naught is 4 millimeters minus mu is 0.1 square into R is 150. This gives me the value of Tf as 2.5 millimeters. That is the minimum possible thickness of the sheet that can be produced in a single pass. Another very quick and small problem that we can try to solve here is the thickness of a metallic sheet is reduced from an initial value of 16 millimeters to a final value of 10 millimeters in one single pass rolling with a pair of cylindrical rollers, each of diameter 400 millimeter. What is the bite angle in degree? Bite angle, I need to find theta. You know that mu is equal to tan theta. Now, if I use the relation draft is equal to mu square R, which means mu square is equal to draft by R, I will put mu square as tan theta, which gives me tan theta is equal to under root of draft by the radius of the roll. everything is given here, T naught, Tf, and diameter as 16 millimeters, 10 millimeters, and 400 millimeters respectively. With diameter as 400 millimeters, I can put the radius as 200 millimeters. Here theta is my bite angle. Therefore, theta is equal to tan inverse of the under root of draft, which is the difference between the initial and the final thickness, 16 minus 10, by the radius, which is 200. Therefore, theta is equal to tan inverse of this value is 0.1732, and this turns out to be 9.82 degrees. This is the bite angle. Just to recall, this is the bite angle. Bite angle is the angle of this length, that is the contact length, with the rollers. So, these were very common problems in rolling, or very simple problem where we were really calculating the draft or the final thickness or the length or the bite angle. Let me also now take a problem in rolling where we will try to determine the power or force that is there in rolling. In this problem, a single pass rolling operation with a 20 millimeter thick plate with plate width of 100 millimeters is reduced to 18 millimeters. The roller radius is 250 millimeter and rotational speed is 10 rpm. The average flow stress of the plate material is 300 megapascal. What is the power required for the rolling operation in kilowatts? You can see in the statement we have been given the value of the initial thickness, the final thickness. Initial thickness is 20 millimeters, final thickness is 18 millimeters, and we have been given the radius of the roll as 250 millimeters. Rotational speed in rotations per minute, it is rpm, is 10 rpm. Also average flow stress, that is sigma naught. Average flow stress, I will put it as sigma naught. We had been using the notation YF bar as flow stress. This is 300 megapascal. I need to now find the power. To find the power, we will first calculate the force and the torque. To find the power, we will first find the force. From the force, we will find the torque. From torque, we will come to power. Now, we know that force is equal to stress into area. This is equal to average flow stress into length into width. So, I need to know the length here first. Width of the plate is given here 100 millimeters. W is equal to 100 millimeters. To find the force, let me calculate length. Length L is equal to under root of R into draft, it is T naught minus Tf. This is equal to under root of radius is 250, T naught is 20, Tf is 18, which this gives me the value of length as 22.36 millimeters. So, I will put this value here. Sigma naught is 300, length is 22.6 and width is 100 millimeters. The force that is calculated here is 670,800 newtons. Now, torque per roll. Torque per roll is given by T, which is equal to force into the average length, that is L by 2, and power is equal to torque into the rotation speed. This is omega, where omega is 2 pi n, and torque we can get from here, which means my power is equal to pi into F into L into n by 60 because we need to find the final value in kilowatts. So it is rotation per minute. I'm just converting it. So which this gives me pi into force, that is 670,800 into length, which is 22.36, into rotation speed, that is 10 rpm by 60, and this is equal to 7.85 kilowatts. This is power required for rolling operation. So rolling operation power in kilowatts for 2 rollers would also have to be calculated. So I will put power for 2 rollers is equal to 7.85 into 2. This is equal to 15.7 kilowatt. So this is the answer. Now I will take one problem each in forging and blanking. There is a problem that is mentioning a circular disc of 200 millimeter diameter is 100 millimeter thick. This is compressed between 2 dies to a thickness of 50 millimeters. Determine the maximum die pressure if the coefficient of friction is 0.1 and yield strength in compression is 230 megapascal. So here I have been given the initial thickness of billet, initial thickness of billet, I will denote it as T naught as 100 millimeters, and final thickness of billet, which is TF as 50 millimeters, 100 millimeter, 50 millimeters. They say determine the die pressure if the coefficient of friction is 0.1. So mu, which that is coefficient of friction, is 0.1, and they say yield strength in compression is 230 megapascal. I will put it as YS, yield strength, or sigma naught as 230 megapascal. I will put the continuity or quantum equivalent equation, that is volume remains same. That is this initial volume, this is final volume. From here we can find the final diameter, because the initial diameter is given 200 millimeter. That means D initial is equal to 200 millimeters. So D final would be D initial, that is D naught square into initial thickness and final thickness. This is equal to 200 square into 100 by 50, which is equal to 282.84 millimeters. This is the final diameter DF, which means final radius is 282.84 by 2 is equal to 141.42 millimeters. We need to find the maximum die pressure. So P max. For that, now we know radius of billet is equal to, I am talking about the final radius RF, this is equal to 141.42 millimeters. Then we have thickness of billet, that is the final thickness, that is given 50 millimeters. Now die pressure is given by PR, which is equal to sigma naught into E power 2 mu by thickness into R minus R. Where this is our yield strength sigma naught. This is equal to 230 into E power 2 mu into R minus R. This small r is equal to 0 because we are talking about the maximum pressure. This into 141.42 by 50, which gives me P max is equal to 404.95 megapascal. So you will use this relation of die pressure to determine the maximum pressure that is there required with the following parameters, with this yield strength, with friction value, and for this dimension. This was one problem in forging. Now let me see one problem in blanking. A round disc of 150 millimeter diameter is to be blanked from a strip of 3.2 millimeter half hard cold rolled steel whose shear strength is given as 310 megapascal. We need to determine the appropriate punch and die diameters and blanking force. To find this, we have to use certain coefficients or certain clearances which are given in the rolling or metal forming handbooks. Now clearance allowances are there, so I will just put it here. Clearance allowance for a specific kind of the blanking. Now this is half hard, cold rolled, and this is steel. Here the clearance allowance is given by AC, that is 0.075, and therefore the clearance is clearance C is equal to AC times the thickness, and we have been given here the thickness. I will put it as T as 3.2 millimeters, the diameter D as 150 millimeters, that is the die opening diameter, and I have been given 310 megapascal as my shear strength. I will put it as sigma naught as 310 megapascal. Now, since blank diameter is 150, punch diameter is blank diameter minus the clearance. Clearance is 0.075 into 3.2. This is equal to 0.24 millimeters. So, in blanking, if this is a sheet and from here the blank is taken out, and there is a punch. This is our punch and this is my blank here. We have clearance here at this point. Clearance is at two sides. Therefore, my punch diameter is equal to the die opening diameter, that is the blank diameter, that is 150 minus 2 times the clearance. This is 149.52 millimeters. And to find it blanking force, what is the force? Blanking force, if you wish to determine, that was what? It was the shear strength, that is sigma naught, into the length into the width in general. Now, here we have got the punch diameter. We need to find the complete force. To find the complete force, the force is around what? This is a round disc. So, all around the perimeter the force is applied. So, I will find this perimeter so that I can put it here. Perimeter of blank is equal to 2 pi r or pi d. This is equal to pi into 150, or this is equal to 471.2 millimeters. Now, force, if I wish to calculate, this is equal to the shear strength 310 megapascals into the length into the width. So, here length is the perimeter which I have calculated, 471.2, times the width. The width here is the thickness, that is 3.2. I will put here the formula as sigma naught into the perimeter into the thickness. This value, this is equal to 467,430.4 Newton. This is the force, blanking force that was asked, part B. Part 1 was the punch and the die diameters. So, these are our solution: the perimeter, the punch diameter, it is all calculated. And die diameter is anyway the given D 150 millimeter, that is the blank, that will be die diameter. With this, I am closing my tutorial session on the metal forming. I will meet you in the next lecture where we will demonstrate the virtual laboratory on metal forming. Thank you.